In organic chemistry, you might find yourself making a molecule like this, a secondary alcohol. But if you've got two different R groups, this is of course a stereocentre because, well, there's an extra hydrogen at the back. So there's four different things attached to that central carbon. And it might be really important to your synthesis to know exactly which configuration you have at that stereocentre. I want to talk through some methods for how you might use Mosher ester analysis to do this. This is an NMR spectroscopy based technique, which can allow us to determine the absolute configuration. Later in the video, I'll show you how to use this on some spectra that I took during my PhD. So the first thing you could use a Mosher ester for is to determine the enantiomeric excess of a mixture of configurations. You can of course use chiral HPLC for this nowadays, so this is very much an old school technique, but I think it sets up some of the ideas nicely. So let's assume we've made a molecule with R1 and R2 having no other stereocentres on them. Say we've done a reaction that makes a mixture of the two enantiomers like this. So these two are indistinguishable by NMR. And what we can do is just derivitize them with a chiral molecule, which is enantiopure. So one way we can do this is to make the Mosher esters. This can be done using a reagent like this. This is methoxy trifluoromethyl phenylacetic acid, or MTPA. And importantly, we use this acid as a single enantiomer. In this case, we can see which one we have. I can assign the usual priorities to define what that stereocentre with a green star is, using CIP rules, that's Kahn-Ingold Prelog rules. The highest priority group will be the methoxy, because we go by atomic number, so that's the oxygen. Next highest is carbon plus fluorines, priority 2. Then carbon plus oxygens, priority 3. And carbon plus other carbons will be priority 4. So we can see our lowest priority group is at the back. And so our numbers rotate like this, going 1 to 2 to 3. Turning this way round, we'll define this as an R stereocentre. I'll just get rid of that working for clarity. Now we need a good way to couple the acid to the alcohol to make the ester. A simple enough way of doing this would be to use a coupling agent such as DCC, that's dicyclohexyl carbodiimide, which has a structure like this. It's just a common way of activating this OH group on the acid and make it into a leaving group. So what we've done here is just converted both the enantiomers that were in our mixture into these two esters, but something critical has happened. Because we know the stereocentre from the Mosher ester was of a single configuration, these two ester products are now diastereomers. If they're diastereomers, they're completely different chemical compounds with completely different properties, and importantly, will have completely different NMR spectra. And if we put the full product mixture into an NMR machine, we can just use integration values, say in the proton NMR, to work out how much of one we have relative to another. And therefore, we can work out the enantiomeric excess of the original alcohols. Now, a useful feature is that they have a trifluoromethyl group on them, which we'll see is incredibly useful later, but for now just gives us a simplification. So we can determine the enantiomeric excess by measuring the relative integration values of peaks in both, say, the proton NMR or the fluorine NMR. Now, depending on how complicated your molecule is, the proton spectrum, you're likely to be doubling up lots of the peaks there. It might get a bit messy. Whereas if you don't have any other fluorines in your molecule, the fluorine NMR can really come to your rescue because the CF3 group on the Mosher esters will just lead to a singlet for the CF3 from each diastereomer. So you just need to look at the relative integrations of those two peaks. You can, of course, use other chiral derivitising agents, but the Mosher acids are reasonably easily available, and this is one of their perks. So once you have those two integration values, let's just call the two esters ester 1 and ester 2, you can calculate the enantiomeric excess just by using those integration values. So this is the integration value of the CF3 peak in Mosher ester 1, take away the integration value in Mosher ester 2, divided by the sum of those two integration values. Now that's all well and good, but where these esters really come into their own is when you're trying to determine absolute configuration of a secondary alcohol stereocentre rather than just the EE. And to show you how this works, I'll just make a new slide. Now I'm going to assume that I've made a secondary alcohol, and by whatever chemistry, I've made it configurationally pure. So just to be clear, we need to have 100% of one configuration at that centre. But the point is, we don't know which one, R or S. Or more likely, we're not doing this randomly. We want to prove that we've got the one that we intended to make in the first place. So being a good synthetic chemist. What we need to do now is take a small sample of our alcohol and do two separate reactions with each enantiomer of the Mosher acid. So we could take the top one and react it with the S-Mosher acid, and we could take a small sample of the bottom one and react it with the R-Mosher acid to produce two different products separately. And the relationship between these products, of course, will also be diastereomers. So they will have different NMR spectra. And what we do is we compare the chemical shift values in these two diastereomers, and it's been shown that the effect of the configuration of the Mosher ester has a predictable effect on the relative chemical shifts of these two diastereomers. Now that might seem a bit odd. So why might that be? Well, as often is the case in organic chemistry, there is a molecular orbital effect going on, that in fact these Mosher esters have a preferred conformation. There are several factors at work here, so I just want to keep this quite general. Firstly, the CF3 group has quite an impact, as often happens when you add fluorines to molecules. So in the general form of the ester, there is a preferred conformation here, where this low energy sigma star, low energy because of all those fluorines at one end, prefers to sit antiperiplanar to this CO sigma molecular orbital. So in this conformation, we'll lower the energy of the overall molecule by forming an interaction between these two orbitals. So what we're saying here is that these bonds want to be antiperiplanar, or APP. Next, as there is for any ester that has a choice, there is a preferred conformation of where it puts its R group, because this oxygen is sp2 hybridized. So for the oxygen, there's a lone pair delocalized in a pi system. That's true for both of these, and that's outside of the plane of the paper. The remaining lone pair will sit in an sp2 hybrid, so either pointing down here on the first structure or up to the top right on the second structure. And there's another orbital effect that goes on here. There's a low-lying sigma star inside the carbonyl, which is well set up to overlap on the structure on the left, but not on the one on the right. So for the same reasons as before, the structure on the left is the preferred conformation. But we're not done yet. There's one final factor that favors a particular conformation here, again on the ester. So just keeping things general, it's also preferred that this CH bond is in the same plane as the carbonyl. So this type of effect is often referred to as allylic strain or A1-free strain, or can be analyzed using the Hauck model. And there's a couple of reasons why this applies. So when you have your other R groups, which I'm just going to represent as purple blobs, it's quite good for this lone pair to just sit in a conformation that's between these. So we want to minimize staggering in this way. But the other important factor, of course, is the other lone pair on the oxygen is in a p orbital and so delocalized into the pi system. So there's already restricted rotation around that CO bond that isn't drawn in our conventional Lewis structure. We can see that by just drawing a resonance structure. Okay, so that's quite a lot to take in with the conformations. Let's see how this applies to the Mosher ester situation above. Okay, so let's take the first structure. I'm just going to put an orange star by it up the top. So this is the diastereomer that was made from the S-Mosher acid. This is the core skeleton that I need to keep in plane in blue. I have the S configuration on the Mosher ester itself, and I'm just using the color there to differentiate whether we're in front or behind of the plane. Now on the other side, we have two R groups, but we don't know the configuration at the other stereocentre. But what we do know is that one of the groups will have to be at the front, which I'll just put as a blob, and one of them will have to be out the back, also drawn as a blob. Now, because this is stuck in a conformation, depending on which R group is on the same side as the phenol group and which one's on the same side as the methoxy group, we'll get a different shielding effect. So the phenol group will have a direct effect on this purple one in front of the plane, and this group shields the R group. Just so we're very clear on the terminology here, this sends this R group to a lower chemical shift. The methoxy group is on the same face as the green blob, and that has the opposite effect. This de-shields any of the signals on that group, so that sends any peaks to higher chemical shift values. Next, I'll just draw in the other diastereomer just to see where we're at. It's the one with this purple star. This is a diastereomer that we made from the R-Mosher acid. So we have the same core structure in the plane of the paper, except this time the configuration on the Mosher ester is going to be R. Now what I'm going to do is keep the blobs the same. So the unknown stereocentre is going to have the purple group at the front and the green group on the back. But because of our stereocentre, we actually get a different effect. This time, the methoxy group is on the front face and the phenol group is on the back. So the shielding and de-shielding happens the opposite way round, all the signals on the purple group will be deshielded and move to a higher chemical shift. The groups on the green blob will be shielded by the phenol group and move to lower chemical shifts. Now, I want to demonstrate how this actually works in practice using some real spectra, because the theory can get a bit confusing here if we're not looking at the spectra themselves. These changes can be really quite pronounced. The general idea is that this gives us enough information to determine what the configuration is that we didn't know on our original alcohol. Right then, so let's see how this method gets used in practice. This is a proton spectrum for a molecule that I made during my PhD. The molecule I made was this one, which of course is a secondary alcohol, which has a stereocentre. So I made this as a single enantiomer, or really very, very high EE. And I want to show you how you can prove the absolute configuration of that stereocentre just using NMR spectra alone. In fact, let me know in the comments below how you'd make this molecule enantioselectively. There are certainly lots of different methods you could try. And while you're there, if you're enjoying the video, please do give it a like. That would be very much appreciated. I'm just going to give myself some labels to assign the peaks. There's 3 different protons on that terminal alkene. Let's just call them A, B, and C. There are 2 protons on the next carbon along. Now, these are actually different because they're next to a stereocentre. We would call these diastereotopic, so I'll give them each different labels. Let's call them D and E. There's a proton on the same carbon as the OH. Let's call that F. Next 2 protons are also diastereotopic. Let's call them G and H. And finally, there's some more on the alpha, beta, unsaturated alkene. Let's call that I and J. Okay, so first things first, let's assign the spectrum of this alcohol just to get familiar with the peaks. It's important that we know that this spectrum was taken in deuterated chloroform as the solvent. So we can see the residual solvent peak here, which we could just use to calibrate the spectrum. It looks like former me was being a little bit lazy, and we can see a few peaks here, just with the arrows. This is some residual ethyl acetate that probably comes from the workup procedure, which I haven't removed fully on my HIVAC line. So I can just ignore these peaks. And in fact, we can largely solve this structure just by looking at the delta values. And then what I'll do is I'll zoom in so that we can see the shape of the splittings. The peak around 7 ppm, the highest chemical shift, that's due to proton I. That's the beta position of the alpha beta unsaturated carbonyl, which will be the most deshielded by this sort of resonance structure. Another quite easy one to go for is J, which is quite clearly a doublet. It also has a very large J value. We can see that splitting there. That's a characteristic of the E geometry of a double bond. So the other ones, A, B, and C, are going to be the remaining peaks that are between 5 and 6 ppm. We would expect their splitting to be slightly more complicated. In fact, we can have a quick predict what we'd expect to see. We'd expect A to couple to C, so therefore A should be a doublet. We'd expect B to be only able to couple to C as well, so will also be a doublet. And we'd expect C itself to be, well, a doublet of doublets of doublets of doublets, which we'll probably just approximate to a multiplet because it's coupling to A, B, D, and E. Now, even just considering that allows us to see that, well, this next peak along is probably C, this multiplet. And so we're looking for 2 more doublets, one for A, one for B. Well, in here, there are 2 overlap doublets. What we can imagine we've got here, the left-hand side of each of the doublets seems to be overlapping. We'd expect there to be a slightly different coupling constant for these. So when we add something like this together, the leftmost peak is going to be twice the height of the other ones. And we're seeing something that looks like this. Okay, off on its own is the peak due to proton F. That's next to our hydroxyl group. And there it is, just below 4 ppm. Again, that's a multiplet. That's coupling to D, E, G, and H. Doublet of doublets of doublets, but it all smushes together and just looks like a mess. So we'll call it a multiplet. This 3H singlet is the OME on the ester. That's just on the right-hand side of the molecule. And the remaining peaks down between 2 and 2.5, well, they're integrating to about 4, and there's several peaks we'd expect in a similar position. This is going to be some overlapping between D, E, G, and H, all of which we'd expect to be multiplets. We could distinguish this further using other NMR experiments, but it's going to turn out not to be particularly useful for us for the Mosher ester analysis. One further thing that we can see here is that the OH appears to be in this spectrum. It's broad due to hydrogen bonding. We can't learn an awful lot from its chemical shift or from its peak shape. because whether or not we see hydroxyl protons like that is quite dependent on the concentration of the sample and the choice of solvent that we have and the substrate that we're looking at. But we happen to see it in here, which is nice. Now, I just want to zoom in on those peaks, just going from left to right. So that's going to involve me losing the structure at the start, but hopefully you can keep it in your head for a moment. We can see here for I, peak shape is a quite clean doublet of triplets. This is the beta position of the alpha beta unsaturated ester, and it's what we'd really expect. We'd have one large coupling constant across the alkene and two smaller ones. What we're seeing there is essentially two triplets where the middle signals are overlapping. Just some other features that are here in passing. On the next peak along, we can see it's not a perfect doublet. There's some tiny extra splitting patterns just here that we can see. That's just some extra long range 4J coupling. The 4J values there are probably less than a hertz. So we're only seeing that effect because I did this on a high resolution machine. Otherwise, we can just consider that really a doublet. You often see extra splitting like this if you're near alkenes, for example. On closer inspection, we can see that C is still just a multiplet, and I'm not going to go any further there. Zooming in on A and B here, we can see that the little sketch shows the overlapping quite well, with the peak on the left-hand side being an overlap. Over to peak F at around 4 ppm. Yep, still going to keep that as a multiplet. There's a lot of overlapping there and nothing much more to learn. And the same goes for D, E, G, and H. So although we could use them as part of a Mosher ester analysis, we're going to need to put some more work in, which I'm not going to propose we do in this video. But for example, you could use a cozy experiment to disentangle this. That's a two-dimensional NMR spectrum that emphasizes coupling relationships. So to take forwards, we'll keep these peaks on the left-hand side of the spectrum between 3.5 and 7 ppm, because they're all nicely separated. They have distinctive peak shapes, and they represent protons on either side of the stereocentre that we don't know the configuration of. Right then, so what I put on the screen now is a duplicate of the original alcohol that we don't know the configuration of, and that's at the top here. And as I said before, we're just going to ignore everything below 3.5 ppm for the purposes of this video, because my computer animation skills are not up to dealing with the messy peaks there. I'll just put the assignments back on. So that's A and B, that's our two doublets. That's these overlap doublets here. Peak C was this doublet of doublets of doublets of doublets, or a multiplet down the bottom here. And then there's the two protons on the alpha beta unsaturated ester. Proton I is the one that's really deshielded and it's at the highest chemical shift, and J is the one in the alpha position, which is this nice clear doublet. What I've got down below is the two diastereomers of the Mosher esters. So this first one is the Mosher ester that came from the S enantiomer of the Mosher acid. And at the bottom is the Mosher ester from the R enantiomer. Now, my lining up skills aren't perfect here, but hopefully we can use the scales, which are calibrated, to see what's going on. So I'll draw as much of a structure as I can determine to start with, just on the right-hand side. Okay, and what we want to do is have a look at the spectra and see if they can let us determine R1 and R2. As a reminder, if an R group sits on the same side as the phenyl group, it will be shielded and go to a lower delta value. If a group is on the same side as the methoxy group, it will be deshielded and go to a higher delta value. And now we just have to look for our peaks. So there have been some changes in general, so we can't compare these ester structures completely to the original alcohol. We'd expect some of the shifts to change around. In fact, that's the whole point of this method. Just keeping an eye on what has changed. One thing that we can note, we've got an extra OME peak, an extra 3H singlet in both of these structures. That's completely reasonable, of course, because we've got an OME group coming from the Mosher ester itself. So that's a good check that that's on. So that's probably the peak around 3.5. Given that the other peak at around 3.7, due to the ester in the original molecule, is so far away from where we've just put the new ester on, likelihood is it's just staying roughly where it was at a similar chemical shift. We wouldn't expect groups so far apart to have a noticeable impact on the chemical shift. One thing that we can note is that the peak that was due to the proton on the original stereocentre that we called F was originally here at 3.8 ppm on the alcohol spectrum, and that's disappeared from the ester spectra. That's, of course, to be expected because we've now put an electron withdrawing group on that hydroxyl group. So the proton we're now talking about, I'm just highlighting in 2 green arrows on each of the structures. That used to be the one we called F. And if we have a quick look at the rest of the spectrum, well, that's probably this one in each of the spectra. I don't recognize that peak shape, and that's in a sensible place for that type of proton. Though we'll note that that proton isn't particularly useful for us in our determination of the configuration because it's sitting in the plane of the paper. We can also see at the very top end of the spectrum, there's some other things that have come from the Mosher ester, which should be expected. These are just the phenol groups at around 7.5, and they'll play no part in our analysis either. Okay, so let's see what's happened to the other peaks. So hopefully you might have noticed that some of the things have shuffled around quite a bit. Let's take the peak between 6.5 and 7 ppm first. That's the one that we've previously labeled as I. And we can see in the top ester spectrum, the peak with the same shape has a chemical shift of around, well, let's say 6.75 ppm. Whereas in the bottom spectrum, that peak is around 6.85 ppm. So we're observing a difference in the chemical shifts for that proton. In the top spectrum, it's a bit lower than the one in the bottom spectrum. Now, actually, we'll notice the same effect if we zoom in on the doublet that we previously called J. In the top ester spectrum, that's going to be around 5.8 ppm, whereas actually it's about 5.9 ppm in the bottom structure. So both of those peaks have moved to higher delta values in the bottom spectrum relative to the top spectrum. Putting in the labels for the other ones, our messy multiplet that was for C appears to be about 5.6 in the bottom spectrum, whereas it's about 5.7 in the top spectrum. So that's actually moved in the other direction. The peak due to C has moved to the right in the bottom spectrum. And we can also see that this has happened to the A and B peaks, the overlap doublets. They've also moved to the right. Originally, they were about 5.15 ppm, and they're more like 5.05 ppm in the bottom spectrum. So now we're pretty much done. We know that I and J are on one side of the molecule, and we know that A, B, and C are on the other side of the molecule. So we just need to rationalize that with our model. And one thing we could do is just do this mathematically, just to be really, really clear. I'm going to define a quantity, delta delta. That's a change in delta value, using both upper and lowercase Greek for a change. And define that as the shift that's in the S spectrum. So I'm going to define that as the top one. Take away the R spectrum, which is just the bottom spectrum. You can do this either way round. We're just looking for a measure of the relative differences here. I just want to find some way of explaining this. If we define delta delta like this, we can see if we have a look at what's happened to R1, delta delta, well, we should end up with a negative number here. And for R2, delta delta will be positive instead. That's purely just looking at the relative changes for each of those structures. So just moving back to our spectrum, the delta delta value for peak I will be approximately 6.75 take 6.85, which is a negative value. And therefore we can conclude that I is part of R1. Now we can do the same for J and find that J is part of R1 as well. And just having a look at, say, A and B, the delta delta value for there is approximately equal to 5.15 take away 5.05, which is a positive number. And therefore this is part of R2 on my diagram. And we can conclude the exact same thing about C. And then, in fact, we're done. So just at the bottom, as a conclusion, we can take our structure. Let's just take this one, for example. We now know which groups are on R1 and R2. So coming forwards, we'll have our alpha, beta, and saturated ester. And going backwards, we have the other alkene. And so we've defined the stereocentre. And so we now know the absolute configuration. I'll just do a quick cut to take the ester off. And so now we infer that the configuration of the original alcohol was just this one in the box. We can define that by priorities again. The alcohol will be priority 1, priority 2 on the right-hand side, priority 3 on the left-hand side because there's less stuff, and the hydrogen will be the lowest priority. Looking around at our priorities, we can see that this will be the R configuration. So in my PhD project, this was quite early days in a long total synthesis. It was important to get this one stereocentre in very precisely because we would then use it for diastereoselective transformations later. And I'll make a video on determining relative stereochemistry in diastereomers. at a future date.